So this is there's the Godfather parts 1, 2, and 3. The not well known, actually best part of the Godfather was Godfather part 4.
Yeah.
This is actually the best part of cryptography part 4.
Yeah.
Little known secret. But yeah, today we're going to be discussing elliptic curve cryptography. Like, what is it? Why is it useful? Why do we care? And then also a few attacks on it. And Sagnik has some challenges to go do. So should be a good amount of fun.
Yeah, at the moment, there are only 2 challenges up on CTFD, but by tonight, there should be at least 1 more, maybe 2.
There are also a bunch of challenges on Crypto Hack, which we award points for on Pony CTF, I believe.
Yep.
So cool. Great. So this weekend we were having cybersecurity careers. I know Thomas, who was a former president of SIGPwny, is coming. I don't know if anyone else is coming. We may have some people live on Zoom. I'm not totally sure. But we haven't done this meeting for, gosh, I think since like 2022, 2023 or something. So this will be a lot of fun. Kind of get to learn about what people are actually doing in the field. I imagine for most of you, your interactions with people at UIUC are either with students, people doing research, professors and whatnot. So, this is all very well and cool and good and whatnot. But it's also nice to kind of hear what people are doing and what jobs people are working in and stuff like that. What you could kind of make a career out of by doing stuff at SIGPwny full time. So this is the meeting flag. You'll learn about everything except maybe the slightly out of context field theory, XKCD. Is anyone here like super paranoid about their cryptography? You're like, like uses GPG unironically. Like I'm not like trolling you. I respect the hustle. I just everyone's pretty content. Okay.
Mm-hmm.
All right. Be careful who you trust.
Yeah. Yeah.
I'm like an I'm like a government not insurrectionist. That's what the people who did on January 6th. I guess like a dissident. I'm just saying, man. Okay, this is good. You don't roll your own crypto, but also maybe don't let the government roll your crypto for you.
I mean, think about this. The government also has to roll out their own crypto.
That is true.
Depending on the frame of reference.
Also consider the NCSA was like, guys, don't do quantum cryptography. Like that's fake. Like it's provably secure. It's fake. Like don't do it. Yeah. I mean, I'm saying this like partially tongue in cheek, but we'll talk about like some curves used in practice later. But there are like these NIST curves that are like, okay, like this is like mainly according to like one person who like developed the competing curve. So there's some bias there too. But anyway, cool. So we'll get started. I think the first thing is just a little bit of math background. So fortunately, this is the most math heavy slide. So if you're going to leave now. I'm just kidding. Please don't leave. So the 2 main things we want to talk about, well really, I mean, it's not that important to what we're going over, but our groups and fields. So group, you have some set and you have some binary operation. And I left some properties on here. You can like look this up on Wikipedia. The real, I guess, like meat and potatoes is like, okay, you have 2 elements in your set, which are part of your group, and you do some operations. So like, for example, we have the integers and we have addition. Or we could have like the integers, mod something, and we have multiplication or something. So, if I add 2 integers together, what do I get? Another integer. Okay, so we have closure. We also have 2 integers. There's some number that I can add to every integer such that I get the same integer back. Well, that's 0. Okay, that's just like our additive identity in this case. Each element has an inverse. If we have a number A, we have negative A. If I have 1, a negative 1, I add them together, I get 0. Okay, good. And it's associative. So I can, group the operations differently. And then the other thing to add on here is that if our group, again, and a group is both like a set and an operation. So if the operation is also commutative, so I didn't like draw it out here, but that would be, I can like switch the order things are done. then we would call that an abelian group. And so when we get into fields, I think I skipped the definition of a ring, but basically, this is like slightly incorrect terminology, but a field, it's like a group, but now you've added on another operation, which in most cases is multiplication. So you have like addition and multiplication. And it basically follows all the same rules, except for something like multiplication, right? Like you don't include zero because zero doesn't have a multiplicative inverse. I'm sure what I told you was not like fully correct. If there's a theorist in the crowd, they'd probably be, throwing apples or something at me. But this is the general idea. Okay, cool. You do not have to like memorize this, just kind of have this in the back of your head. Okay, so now what are elliptic curves? This is the fun part. This is like the visual part. There is this QR code just is like a Desmos for playing around with different variables for elliptic curves. So like it's not necessary to scan or anything. If you're kind of a visual learner or you just want to like actually intuit what's going on, that can be a really helpful example to just like drag around the parameters for A and B. Mathematicians are like really terrible at naming things. This is really no exception. So an elliptic curve is basically just, this is not like the full set of elliptic curves, but this is kind of the set of elliptic curves we usually care the most about. I think it's like Weisser-Strass form. I have no idea who Weisser-Strass was. Probably a really famous guy. I don't know.
Yeah.
Oh yeah.
Very he made a lot of contributions to algebra and also like real analysis. He kind of standardized this specific form of cubics that kind of look like kind of like a frame of like mitosis or something. I mean, it looks like there's like a cell kind of like pinching out. Most classes of elliptic curves that like we deal with will have this general structure, and you'll see on like the next slides, these have some pretty interesting mathematical properties, which is why we use them.
Yeah. If you're wondering, like, why don't we care about, I guess, like polynomials of smaller degree or higher degree? Polynomials of smaller degree are like basically trivial to solve and look at and whatnot. Like are just not very interesting. And polynomials of higher degree are just I guess untractable.
Yeah, they're a lot harder to like do operations on.
Yeah,
like
yeah.
This kind of thing.
So we'll talk a little bit more when we go into like using these for cryptography, but the impetus for using something like this is like when you actually are using this to do like real life cryptography on real life hardware, this is very performant, like very fast. Oh yeah.
Do elliptic curves have anything to do with ellipse? And if not, then why are they called elliptic curves?
Yeah, okay. I did read a little bit about that. My understanding is like not really. I think it has something to do with like tangent points of curves because that's like somewhat important. I don't think. I think like from the albeit limited amount of like I've researched into the etymology of elliptic curve as the name. It was like that was the name that stuck, and I don't really know why it was chosen, but it's not.
Correct me if I'm wrong, but I'm pretty sure the elliptic curve came from a bunch of mathematicians back in the day, including Weierstrass, studying the elliptic integral, or pretty much like calculating like a generalized function for like what the arc length of an ellipse would be. So like again, I might have like mixed a couple of details like here and there, so feel free to fact check me, but in general, like that's where like the elliptic curves came from like studying the arc length of
I guess like how would people be able to do that for cryptography?
they just fucked around with them. They just honestly a lot of this had to do with like finding out like certain properties that when like you take like say an arc length between like some points of an ellipse, eventually like on the curve here, that kind of translates into like an interesting transformation that you could do pretty easily through like that. And like of course like what cryptographers want is something that I could easily like go one way in. But like if I were to like try to like reverse that transformation into something, okay, it becomes suddenly a lot harder. And I guess like from experimenting with elliptic curves, mathematicians eventually figured out that those properties checked off. So, yeah.
I mean, people weren't doing like elliptic curve crypto in the time of like Weierstrass. But I believe it was known that they had these kind of trapdoor function properties, like well before, I guess like the 80s, 90s.
Yeah, something.
It's kind of like probably the early 2000s, like when elliptic curve cryptography started taking off. Okay, so we've talked about a curve. You have a nice picture. We love pictures. I love pictures, at least. We want to talk about our kind of two main operations. Again, we're talking about fields and operations. These are the operations we're getting into. So there's point addition. So this is slightly non-intuitive. So the picture really does help here. But we have 2 points on the curve, right? So which is just like, two like XY coordinates, which is like Cartesian space or something. And we want to add them together. And the important thing I think you should know about like, I don't know, abstract algebra in general is like the operations are like just completely arbitrary, basically. Like you just choose them however you want, such they have the following properties. So, if you think, oh, we'll like, we draw the line and then we should use like the point where it intersects, like, no, you're doing it wrong. You we define it in a way such that it ticks all the boxes. Yeah. So if we have 2 points P and Q that are solutions to our curves, like they're points on the curve, if we want to add them together, we will draw a line through them. And again, there's some cases, but just like assume the case on the left here, right? We have 2 points on the curve, we draw a line through them. That line will then intersect the curve, right? We take that point and we reflect it over the x-axis, which generally speaking, again, because this is a cubic function, like you can also just write like minus the point and you get the same thing. So if I have like minus r, I just mean this point down here, right? And then there are a few edge cases which are like good to keep in mind, are pretty intuitive when you think about it, I would say. So if P and Q are the same point, well, like there's technically an infinite number of lines that can pass through the same point. So we just kind of define that to be the tangent line at that point on the curve. That's our like P and Q basically, which is what you would get if you took the limit as you moved P and Q closer and closer together. Other corner cases include if P and Q essentially form just a vertical line, right? Well, then you obviously have no intersection there. Well, there's a few cases in which you don't have an intersection, like a third point where your line will intersect. And in those cases, you basically define this point at infinity, which I think in literature is usually called O. And this kind of acts as your identity element for point addition. The idea being, if I have like a line like this, PQ, right? We add that we get the identity. Same thing here. If you have P and P, where we like move P and Q on the curve closer and closer and closer together until at the same point, we're also going to get the identity O. And then also in this example here, we draw a line through a P and a Q, but like you can kind of just tell like that's never going to intersect another point on the curve. So that'll that also intersects this point at infinity O. So I don't know, maybe if you are familiar with like hyperbolic geometry or other like projective geometries and stuff like that, this is a similar idea where you just have like you have a point at infinity. But if not, you can kind of just take that at face value. Any questions about this before we move on? Like the general step of point here, line, reflect.
Yes, Nikhil?
So, we define addition with the for like, not the point on point, for example.
If I have the point at infinity and some point. Yeah. So that would be because it essentially acts as the identity. You would just get the point back.
Is there like does that still work with the whole drawing lines idea, or is it fine?
Right, because in the case where you just have one point, I kind of see what you're saying. Yeah, the tangent would intersect. I actually am not sure in that case.
Yeah. From like a drawing perspective, it does seem like the intuition breaks because I mean like having like a point that's at infinity and then like adding the point kind of like fails because at that point you're still, if it like is only tangent at infinity, you kind of like the only place at least in this curve example where it's able to be possible is on the right side here. where like P is all the way at the edge. But in this case, P is its own inverse because of like that thing happening. For like I guess like in that case, for like our purposes, you could consider that point at infinity as like the identity operation for now. But I'm pretty sure there's like a more rigorous way to like posit this. Maybe with like the general structure of elliptic curves. Although
It's like the third.
it's like off screen, it's happening
It's out of bounds.
out of bounds, exactly.
No out of bounds reads or writes allowed except to that point.
Yeah.
Did you have a question too, or?
Yeah, but I would add it to 0. Especially for like the first image. Like, are you taking the y-axis for the x-axis? Like, what are you're taking the y-axis that is right?
Oh yeah. So yeah, that's a good question. So this is like a little bit misleading. This isn't, I guess, if we were to do, okay, just ignore the R, and if we were just to do the addition P plus Q, right? We have these points P and Q, we draw a line through them, and we get to this point R, but then how we've defined point addition, right, is we actually like reflect it over the x-axis. So we get this other point down here. And then when we add that point to R up here, right, we get this vertical line, which we said like that equals the identity at the point of infinity.
Yeah, technically, this image isn't really I guess like the best way to like show this. But like, well, what this is basically saying is that like if you take just any 2 points P and Q, draw the line through them, the point at which it intersects R is actually like the additive inverse of P and Q. So those 3 points together would be 0. So the way you get like back whatever like the actual point R is by like reflecting it across, because that would essentially like negate it. So if I took like P and Q, the point up there would be negative R, but if you reflect it down, that's like the actual result. So like in general, if you want to like add 2 points, just like take like the 2 points, draw the line through, wherever it intersects, reflect it down. And you'll get one. Yeah, it has to do with the formula that it happens in. The proof I didn't exactly rigorize here, but it generally like that's where the property like follows. Yeah,
Yeah.
precisely.
So again, the point at infinity is kind of like a trick we kind of like pull out of our ass or your sleeve, depending on if you're giving this talk to middle schoolers or not. Yeah, source, trust me, bro, it works. If not, like go on Wikipedia and like there's like a full flesh out proof and everything. Okay, so that's point addition. And by the way, if again, you can scan this QR code or just like look up elliptic curve Desmos, and that provides like an example. You can drag lines, you can do point addition, blah, blah, blah. Okay. Point addition is kind of important to do scalar multiplication. Kind of like you probably should know how to like add 2 numbers before you learn how to multiply 2 numbers. Because again, like what is multiplying if not just, you know, repeated addition? So, and again, this is a scalar multiplication, not like multiplying 2 points on the curve. We're just saying, essentially, if I have like some number n and a point on the curve, and we're like defining the scalar multiply operator as just like add that point n times, like to itself. Not like you would have n plus 1 points if you added that n copies to itself, but you get what I mean. Like I have, you know, q plus q plus q plus q for nq. Sometimes you'll see this denoted with brackets over the scalar to kind of denote that it's a scalar. Other times you won't see brackets. Usually the points are capitalized and the scalars are lowercase, but it's usually clear from the context. But in this example here, right, if we were to do 2p, right, 2p is just p plus p. So that's kind of the exact same example we saw in the previous slide, where in this example, like again, it's the same point. We get minus q, we reflect it, and we get q, which is the same thing as 2p. So this scalar multiplication is going to be kind of the bread and butter of what we're actually doing for cryptography. So any questions before we move on from elliptic curve stuff?
Yeah. This is not actually a field that it's like vectors or ironing.
Yeah. You're right. This is not a field. We are going to, like, in the next slide, we're going to talk about how we were like doing this over a field. Yeah, but you're right. You're totally right. Like this, all like this is like over the reals. This is not at all
Not a-
discrete.
Say vector space over here.
Over the reals.
Yeah, your solution space is in R2.
No, I mean, your vector. And your like, this operation is.
And if they're integer points, sure, I think.
I like in an abstract sense, like you can just define like, well, like, yeah, it's like a couple of reals, which you could say that's the same thing as a vector, right? As long as you define your operations accordingly.
Like, other sides of the
Of a vector space, and like inner products and stuff. I have no idea. I don't know. Yeah, I don't know. Presumably, yeah, maybe you could define a suitable inner product. Because it was also a generalization, just in like an abstract Hilbert space, but. Okay, so to your point, this is not actually a field, right? This doesn't obey all the properties. Moreover, it's not a finite field because there's an infinite number of solutions to the curve. So what we want to do instead is, okay, so this looks like very, very, very random. But this is kind of where we go from geometric reasoning to very much just like algebraic reasoning. That instead of worrying about the entire curve, we are essentially only going to worry about the points on the points on the curve, so the solutions to the curve, which are in some finite field. And again, the definition of a finite field is like not like super duper duper important, but like again, basically you have some set, and then you have two operations on that set that'll base on properties. It's kind of like, okay, if you know what a group is, it's like a group with two operations. So on this slide, we have this this elliptic curve, and then we have the same curve over the finite field for 61, where 61 is a prime. So we, again, if you just think of like, integers mod 61, we have kind of all the same, properties, inverses, identity element, closure, yada, yada, yada. And then also commutivity, which is important for this. But again, because it's essentially like modular arithmetic, it kind of gets compressed here. You guys can see there's a lot of empty space here. There's a lot of points here. That's the general idea. We're gonna not show as many point diagrams from here on out because like it's not very conducive to understanding or meaning in any sense.
I guess the biggest takeaway you should see from here is now you're beginning to see like kind of the structure that cryptographers really like to look for, is because like the moment I did take it over like F61, suddenly like the points that you see look a lot more random and like harder to actually like find out like where you're actually going with. And that's something we do like as cryptographers. I mean, like the structure would change if I were to increase 61 to like, I don't know, 2 to the power of 32 plus something as a prime. Like the larger the primes get, the more confusing it should become. And this happens to follow that structure.
Yeah. And over your field, you can find elements like the field is a very large order, the cycle is very long, stuff like that. The other important thing to note here is that, again, because we kind of defined our point infinity sort of like abstractly, we define this field as all of these, points on the curve, but since O is technically not on the curve, we have to like also add in the point at infinity, just like a small footnote. Cool. So, phew, done with the math. Fantastic. Now onto the cryptography stuff. So, and I think I forgot exactly what we did in like crypto 1, 2, and 3. I think crypto 3 was block ciphers. So mainly, I guess it's kind of coming back to crypto 1 and 2. We're doing asymmetric cryptography. Okay, like what are we looking for? We want to establish some sort of shared secret that does not involve, like physically, going to a Linux conference and sharing our GPG keys, because like I would absolutely die that those people do not wear deodorant. Like it would be terrible, man. And not worth communicating securely. I would trade my privacy for not having to do that in like a nanosecond.
Yeah. Yeah.
Just
Yeah.
kidding. Just kidding. So what we've discussed in the past, which no worries if you don't know what these are, this is gonna be a very brief review of like RSA and Diffie-Hellman. We are using what we were talking about earlier, like these one-way functions, these trapdoor functions, to essentially Alice and Bob agree upon some scheme. They exchange things over the wire, and we're saying that some eavesdropper is allowed to see what they're exchanging. And they can somehow form some shared secret such that even if you know, I mean, in the example of Diffie-Hellman, for example, even if you know, G to the A mod P or G to the B mod P, you don't really know anything unless you also know Alice or Bob's secret, in this case, A and B. So we're also going to explain Diffie-Hellman like in just one sec, but again, it's the same idea of like these two numbers are equal. Alice does some process, Bob does some process, and they get the same thing. They get their shared secret. But for the numbers across the wire, GA and GB, you don't really glean any useful information, because finding this A or this B given that information is very hard, is believed to be hard. Yeah, so I guess that was just text on the screen. Here's more text on the screen for Diffie-Hellman, which is not really the interesting part here, because we're here talking about elliptic curves. But you can kind of think of it as as like mixing colors. So like this is the common paint. Alice and Bob choose their secret paints, and then like given the orange or the light orange or the cyan, go Illini, who like you can't find this red and this green, or this red and this, I guess, more cyany color. And then you add them together. This comes back to like the commutativity thing, which is important. And they both get the same thing at the end.
Yeah. Yeah, so this is like the classic one you guys saw in like Crypto 2, right? Pretty standard. The reason why this works is that this will eventually both be G to the power of AB mod P together, and that's like shown through like the color mixing. Now, yeah, that's cool and all, but it's frankly a little boring. I mean, this is a pretty dated way to do it, and there's a lot of like more practical attacks on old Diffie-Hellman that you saw in Crypto 2, and the elliptic curve variant tends to at least tries to attempt to fix a lot of those. So this is the new Diffie-Hellman. So in like the same spirit as before, instead of choosing a prime generator P, instead we choose some elliptic curve point like G as like a generator within like that curve over that finite field, and then some very large prime P. And this is all through like an agreed on like elliptic curve. Normally like these curves would be what we call like NIST standard, and NIST is kind of like the big brother here who like decides like which curves are actually secure based on like studies. And now the thing that Alice wants to do is Alice does like the scalar multiplication we talked before with her same like secret A. Now she scalar multiplies it with that point G to compute AG mod P. And Bob does the same thing with B. And these are like our public keys. Now, once Bob receives, say, Alice's AG mod P, you could do another scalar multiplication on top of that, where Bob computes B times A times G, which is AB mod G. But because like over like this field here, the operation of scalar multiplication is pretty much commutative. You'll have AB multiplied by G is the same thing as like BA multiplied by G mod P. And that basically like establishes that same like Diffie-Hellman exchange that we saw before. But instead now we're doing it with the elliptic curves. So it has the same properties we talked about before. Yeah, but
On the selected curve, how do you know that's prime? How do you know it's on the curve?
yeah, no. P is simply like a prime, not necessarily like a point on the curve, but like the prime has to, it's like the prime order we talked before. Like you remember seeing like the curve, and then like you took it like over like the field F to the 61. Yeah, P is 61 in this case. Yeah, so that's like the prime order that you're taking it over. And the way you select the prime order is again a little bit of math. There's some like properties that they have to hold, such as like if they are smooth primes, for example, or if they are like sufficiently large, they'll have different properties under which like this curve finds. And it turns out that there's a lot of practical attacks you can do if like say the prime is not smooth, for example. You could find papers of these. So they have to hold some properties. for
Yeah.
this to happen. Yeah, Nikhil?
So I guess aren't these basically saying that we will be after in the.
Yeah, like FP. pretty much.
Yeah, the generators for a curve are just like a property of that curve. There are multiple, I think generally speaking, and like in practice, like a curve is standardized and you agree upon what generator you're going to use beforehand. But again, the curve and the finite field pairing is like, that's an important thing. Those go hand in hand, yeah.
Yeah.
Any questions on this? You have Diffie-Hellman, place, Japan.
Yeah.
Oh, sorry, place, finite fields.
Yeah.
Or elliptic.
So just on two numbers by the same P, they will converge. Like, how do you guarantee, I guess, P and Q are the same intersection? Like, what's the-
I think in this example, this is P plus Q's are. I don't think this is this showing scalar multiplication. I don't think this is showing scalar multiplication. I think this is just addition. But like this picture is more showing just like, you know how we did like just point addition earlier. This is
Yeah.
showing point addition in this finite field, right? So like the lines wrap. That's like, you know, we're doing modular arithmetic.
Yeah, and the thing is that this is gonna keep happening in order to do the actual scalar multiplication that we see over here. Cause like that's like the basis for this to happen. It's just that it also like has the analog here with the finite field. That's like what the picture's for.
Right. So like if you were to draw the line through P and Q, you go through and like, you know, this line isn't hitting any of these points, and then suddenly it hits this point right here. And then, you know, we take the, you know, negation of that point to get the actual point. And we know that these points will always exist because of the properties we established earlier, that like this is a finite field, so it has to obey XYZ properties. We didn't really prove that.
So like
thoroughly,
sources
but,
again, trust me, bro, but the proof does exist on.
like because it is a field, like this always works.
I guess like. You're basically doing modular until you get R, take the inverse.
So it's a very good question. What is the point, right? Like at the end of the day, we want to like buy things on Amazon and like share Harry Potter fan fiction, right? The point is we want to be able to have some shared secret, which we, you know, we can do AES and then, you know, life is good. We need to make sure that like no one else, I know that, Sagnik knows it, and JK Rowling like never ever knows like what we're writing about Ron Weasley. Okay, like that should never get out. That should never see the light of day.
Yeah. To be a little more formal, the one weakness, and I think we did talk about this very briefly in Crypto too, though I'm not sure. The classic old example of Diffie-Hellman is actually susceptible to a man-in-the-middle attack. Via like where you are able to like listen to what primes are sent, and you could like more easily manipulate messages this way. The elliptic curve structure has the added benefit that now JK Rowling cannot snoop in between and read my Ron Weasley fanfic. It's not possible.
Right.
to do this.
Actually, I mean, you still should, for any classical scheme, you should be able to do man in the middle, because you can just think of it as Alice and Bob and Alice, but in the Bob and Alice in the middle.
I mean, yes, in theory, you still can. It would just be a lot harder as opposed to like simply taking like an exponentiation.
Yeah. Okay, cool. So going on to, again, like this is the important part, is that like this is a hard operation. This is believed to be hard, because if it wasn't, if given, you know, a scalar multiply AG mod P, if we're given that information and it's easy for us to get A, like we're cooked. We can't do this. Some mathematicians like really sad because his PhD thesis isn't now like worthless.
Yeah.
The important thing is this discrete log problem, which is, you know, the same thing that we were talking about in RSA and Diffie-Hellman, just now on elliptic curves. So like this also was like slightly problematic for quantum computers, but like no one's like proved it yet. But you know, again, you know, given the you know, D times P, you know, it's essentially hard to find. If I give you DP mod the prime over the field we're doing things over, it's hard to find D. That's the general idea. And P, important to know, like P is this generator point. That's known to everyone. That's known to Alice, Bob, the attacker, right?
Yeah, in the prior slides, this is basically G.
Yeah.
We've discussed before. So it's hard, given that like you have G and the target point, it's hard to like see how many times you had to multiply G in order to get to D. That's the discrete log assumption here.
Yeah.
In this case.
Like to rev this, it would take to do this like naively, it would take exponential time.
Peak depth of the universe.
So yeah, like as an example about like reversibility, like if I told you like what was the move we took to get here? I don't actually think it's like this is fully, I guess the more appropriate question would be what was the sequence of moves? I think this is also like not, this is a set of solutions, not like any one solution. But you can imagine, if I, roll out the ball, the billiard balls, and then I like, it's easy to like take a pool cue and like do it, right? But it's very hard to figure out what was the action with the pool cue I did to get the state. Pool may not be like a great example because like from a physics perspective, like there's probably many different ways I could make the state, but don't worry about that too much. Yeah, this is more stuff about discrete log.
Yeah, sure. This is like the main conditions under like which the assumption holds. And the idea is that if like I make D sufficiently large enough and I keep it secret from like attackers, then because of the D log assumption, I cannot compute it easily. And because it's large enough, now like it'll take a non-negligible, by which I mean exponential amount of time to like complete. So if D is known though, such as like the two parties within like a key exchange, then an efficient method to compute DP is required so that I don't need to take an exponential amount of time to actually like send the message as like a one way. And the thing is, if you do happen to know D, then there is an algorithm that you could use to get to the target point, and that's the double and add algorithm. So the idea like from before is that we could have continuously like taken the point that we had before, and if we had like the tangent line on that elliptic curve, we could essentially compute the double of that. And then if we wanted to like repeat the addition, we could just like add it to itself again and like keep on like doubling and doubling and doubling and then like adding to get like large amounts of like scalars. And this is kind of like the overview of the algorithm here. I think in the next slide, I do walk through it a little more intuitively. So, well, let's say like your prime is relatively small, something like 13. The binary representation of this 13 would be a 1101 over here. So I'm going from left to right here. So if the first bit is 1, then I compute t plus t. Now I initialize t in like the algorithm to 0, so this just does nothing pretty much. And then because the first bit is 1 after that if statement, now I'm checking whether or not like if the bit is 1, then I now add p to it. So in this case, I do t plus p, and that's 0 plus p, which eventually gets to p on that point. The second bit is 1 again. So I go through that first branch again where I double it and then add p to itself again. So I get t is now 3p. The third bit is 0, so I just want to double it. I don't need to do anything else. And I do t equals 6p. And because the last bit is 1, now I double it again and then add p. So it becomes 12p plus p, which is 13p. And because all I need to like, the complexity of this really matters with like how many bits that scalar is. It scales very well because now I could just take like the log of that very large scalar. And I could have something like 256 bits or like 128 bits in order to like do this double and add. And that way I could very easily calculate the target point. But because of the discrete log assumption, it would be very hard to actually go back because you'd have to solve the discrete log problem. So this establishes it as like a one way. Any questions?
The general idea is like this is it's fast to do, it's fast to compute, but like very hard to invert. Again, like why do we care about like using elliptic curves for like we've essentially established, okay, we can use elliptic curves for the exact same thing that we were doing with just like regular integers, mod p with Diffie-Hellman. So like why do we actually care about like this added step? And like the reason is like practically like it's really fast. It's really fast and it's also smaller. Like you can achieve comparable security what you could get with like I think on the bottom this is like 3072 bits RSA. And the above curve using ED25519 curve, that's I think only 256 bits. So I mean, just practically speaking, we're sending fewer bits over the wire, which is a good thing. It's also faster to compute this, especially when whenever some new cryptography system gains adoption, you get special performance cores on your computer, and we'll talk about this in like another slide, but basically like the curves people use in practice were specifically chosen with the property that like they are very easy to compute and they're very fast.
They also lend themselves extremely well to specialized hardware. Like I
Yeah.
could make like an ASIC that immediately computes like the key over here, and I could just have like my Bitcoin mining rig just do it or something like that.
Yeah. So this is like great in practical terms for usability. So as an example, this is TLS 1.3, which I think is like not like technically, I don't think all sites technically use TLS 1.3 now. I think some are still on like legacy RSA and stuff, but this is probably what you're using on most websites. I believe that the curve in TLS 1.3 is, I don't think it's always ED25519, but like most of the time it is. I'm not sure if it's like fully configurable, but the idea being, okay, like if TLS, we're we're talking on a website, it's like an actual standard used on your computer over the internet and everything. The curve here, so again, this is like bigger than we've been talking about, and the field, instead of being 61, it's this prime, which is 2 to the 255 minus 19, hence 25519. And then this is the equation for the curve. It is not like super duper interesting, but the main idea here is like, okay, we chose a form of an elliptic curve, which if you notice very carefully, like this is technically different than the other. It is a different form than the ones we've been talking about previously. And the reason we chose this form was because like it's really fast. It's got like a Montgomery form curve. It's really fast. And then we kind of like choose all these other properties that we want of our elliptic curves. Now we have some like set of elliptic curves. We search that space and we just kind of say, okay, like no. Okay, yeah, that one's good.
And it happens that the coefficient there was 486,662. And it was just kind of arbitrarily found through that process of like narrowing down which items in the set should choose those properties. But this has not been pretty much like, it's pretty secure now if like you're able to like use it in your website. Before, there used to be another curve in contention that was generally considered secure, SP2025, I think.
Yeah.
But it turns out that not all of these properties were there in SP521. And it turns out under certain conditions, you could get a 9-bit advantage on like the nonce used. And for EC, for what we'll see later with signatures, that was good.
Yeah. So the how to choose safe curves, to clarify, that link is written by the same guy who like published ED25519. So like pick up like a slight grain of salt, but generally speaking, there's like a little bit of like around NIST curves, but it is technically like the federal standard in the United States. So like I don't think they're bad per se, but if I were to tell you what to do, I would choose 25519. Okay, yeah.
So now we're almost reaching the main thing. So I just really wanted to cover signatures real quick. So as we've seen with like elliptic curve Diffie-Hellman, I'm able to like establish a communication channel across two parties. But now, well, what if like I'm like some guy and I'm talking to like this new stranger that I found, and I'm like, I don't actually trust that you're the person who sent this message. So how am I able to like verify that you're the one who actually sent this message? It turns out that there is a mathematical way we can do that. And that is using the private key to sign the message. So the idea behind signatures is that anyone who has the signer's public key can decrypt the signature, recompute whatever like the original message's like hash was. The hash functions are always public, so I could do that. And then if I'm able to like check the signature message and like the hash of like that, and I could then compare the two hashes, and like if the hashes are the same, well, hashes are pre-image resistant, so hashes are essentially fingerprints. So if the fingerprints match, hey, this must be that person. So over here is kind of like the Alice Bob analog over here of what I just said. Alice's private key was used to generate like a signature there. Of course, you cannot just put her private key there because that defeats the whole purpose. So there's a couple of like extra steps she had to do to generate that signature, but essentially it's based on her private key. So then if Bob, who already has Alice's public key, is able to do like a verification algorithm to basically retrieve that fingerprint and say, okay, this was Alice. So this is a way we could do authenticated transactions, which is again very important because that's how like you have like bank transactions and your Bitcoin isn't stolen. and things like that. Yep. So this is kind of like a very high overview of ECDSA. So over here, the private key is DA for Alice and DB for Bob. Although for now, we could just focus on Alice with terms of signing. So in this case, Alice here is the signer. And let's say the message over here is hello. All she has to do is go through the signature algorithm to generate the signed hash with hello. And then Bob is over there with like a verifier who's able to check the signature that was generated from Alice's private key and then return whether or not like it was authenticated to be Alice. So this is like the high level. Yeah, I sort of lied when I said there wasn't going to be more math because this next slide is the math. So well, what happens here first is that the hash is calculated. Normally, this could be something like SHA-256 or Ketchak-256. Some hash function that's generally considered good and most importantly, like pre-image resistant. So let H here be like the leftmost bits of E, and LN over here is selected with regards to like the group order N. So it's a very specific amount of like topmost bits that are there. So then I choose like a random number K within like this range. This is what we call the nonce. And then I calculate some point in the elliptic curve. This is all over elliptic curve that's known. And that's going to be kg over here. And then I calculate some r over here, which is the first part of the signature, to be that first coordinate mod that order n. Now, if r is equal to 0, then that means that the nonce was not valid and it could be broken. So I keep on generating this nonce until r is non-zero, and s, which is the inverse operation of this mod n, is also non-zero, and that together packaged would be the signature. Going beyond the math over here, the basic idea is that the DA over in like the S part is the private key before, and S is just a transformation on that. That's essentially irreversible mod n. So I have something that is a function of the private key without actually giving out the private key away. And that forms like the signature. That's kind of like the main takeaway from this. Is everyone with me? Perfect. Now for the verifier, Bob, let's say that he's able to get that signature from before, which is RS. Now, what Bob would want to do is compute the hash of the sent message, which is H of M again, and H is obviously public. So Bob is able to do this. Now, let's let H be the LN from before, like the leftmost bits of that message. Now, we're kind of able to slightly go the reverse here. If we compute like the inverse power mod n, we get C, and then using Alice's public key, which is QA over here, he's able to calculate some point on the curve x1, y1, which is u1 times g plus u2 times the public point QA. And he's able to ensure that, hey, this was not 0. And if that's true, then you go on to the next step, which is checking that the first coordinate mod n was the r that you got before. And if that's true, the signature passes. So that's kind of like the verification algorithm for ECDSA. And these two together would be used with the elliptic curve key exchange that we studied before in order to like create certificates or like sign messages across the same channel. Now, we kind of ran out of time here, so I'm not going to be able to cover that many attacks on slides, but there are a lot of good useful papers with like regards to say the internals of ECDSA. For example, like you could probably think of some from like the example I said. Sometimes like the nonce generation with like K could be a little weak because we're ideally still choosing like a random number. But if like the RNG isn't like properly good, for example, then there's some like determinism to like what K could be. And from that, you could construct an attack. Or sometimes even K could be straight up fixed, which is a nonce reuse. So there are also attacks like that. There should be a nonce reuse challenge up there on the CTFD platform. So you could do that. But another good one is like if the generator's order is tiny. this is not good because if it's true, then there are algorithms out there that can basically solve the discrete log problem in square root of n using like stuff like baby steps, giant steps, which is like an internal algorithm. I'm kind of black boxing it here through the use of SageMath, but essentially you could kind of follow this general like order over here, and this runs in square root of n runtime. So it's relatively fast if like your order is small. So in like CTF challenges, you could kind of use this general like Sage Math tool to solve some elliptic curve challenges. In general, like the main resources you want to like pay attention to are like Crypto Hack, which teaches everything I've said in a lot easier detail. It also has a lot of good challenges for like getting used to what elliptic curve crypto challenges are like. The notes we used a lot for this lecture are from Professor Ben Lin. He has some good notes on elliptic curves. There's also like some white papers on how you would implement ED25519, which you could look at, and they also have some details, I think, on internals that
Yeah.
will help you understand better. And then visualizing elliptic curve cryptography, because visualization is good, at least for me.
So I guess like broad strokes conclusion, we've defined this mathematical tool, elliptic curves. We're using it to do cryptography more or less with the same properties we're using with RSA and Davy-Hellman. We have this hard discrete log problem. The reason we care about this in the first place is because it's fast and performant and smaller over the wire. Some of these attacks, like when we say again like generator order, we basically mean like there's not the largest number you can multiply the generator point before you get back to itself is like actually not that big, even if like the finite field you're doing the curve over itself is.
Yep.
Other attacks which are kind of beyond the scope of SIGPwny because they're pretty advanced, are like cache, like side channels and timing attacks. With
Because
again,
it is in hardware.
yeah, because it's all in hardware, and like you can like if you implement your scalar multiplication naively, right? If I multiply by a dB, which is bigger than dA, like it'll take me longer to do that, right? If you do it naively, like there are algorithms to not do this, but if you return super quickly, okay, maybe the scalar which I'm multiplying my point by is actually quite small.
You heard that, embedded team?
Yeah.
Yeah.
There, I believe there are like in actual implementations, there are ways where you can essentially like always make sure you take the same amount of time.
Oh, sure, yeah.
Yeah, but you're absolutely correct. Like if not implemented correctly, like this is definitely vulnerable to a side channel.
Yeah, because it'll always take the
Yeah.
amount of time.
Again, shared secret when we have we want to like do secure communication with signatures. We basically just want to make sure only a person who had this message and had this private key would be able to generate the signature, and I need to be able to verify that using their public key.
Yeah, there are a lot more like transaction proof stuff that I would want to cover in like a way later meeting than I do like multi-party computation. But elliptic curves does also appear with those two because of the properties we talked about.
Okay. Cool. Really quick before we run out of time. Next meetings, again, as we said earlier, career in cybersecurity. It's gonna be a lot of fun. There's gonna be some people who are now in industry who were previously from SIGPwny are gonna be there. Come to that. And then also next Thursday, Adarsh is gonna be teaching password cracking. So again, also a lot of fun. And yeah, here's the flag again. Again, these slides will be posted on the website and on Discord. Any questions before we kind of head out? That was kind of a long meeting. I have a lot of questions about, life, philosophy,
Backdoor encryption.
when do humans die, all that good stuff. Is P equal to MP? Yeah. Well, we if it is, you can ignore whatever, everything we just talked about and go do something more interesting with your time. Okay, cool. We'll be around for a few minutes to help with challenges. I think purple team is meeting T-5 minutes. So
Yeah.